Hi, this is Mrs. LaBarbara. This is AP Physics Chapter 12, Gravitation Video 4. Today's topic is satellite motion. The objectives are no gravity is the only force acting on the satellite. It provides the centripetal force to keep the satellite in orbit. Understand that circular speed of an orbiting body is dependent on the radius, not the mass of the object. To understand the relationship between circular speed and escape speed, to be able to relate the speed, orbital period, and the mechanical energy of a satellite in a circular orbit. A satellite is a projectile that is launched at a great speed so that it does not land on Earth but goes around Earth. Trajectories 1 through 7 shows the effect of increasing the initial speed of launched projectile. As you can see, here's 1 and 2 would have been complete if all the mass is concentrated at point C. Now 3 and 4 are closed orbits called ellipses. Trajectory 4 is a special case. It's a circle, a special case of ellipse. Trajectory 6 and 7, those are open orbits. These are the trajectories that escaped Earth's atmosphere. That means the total energy for the object in path 6 and 7 either is greater than 0 or equals to 0. Satellite for circular orbits. So a circular orbit is the simplest and also an important case because artificial satellites, as well as planets around the sun, have nearly circular orbits. Since the only force acting on a satellite in a circular orbit around Earth is Earth's gravitational force, which is directed toward the center of the Earth and hence toward the center of the orbit, the satellite is in uniform circular motion with constant speed. So the force is toward the center, acceleration has to be toward the center. We know in uniform circular motion, V is tangent to the circle, so A is perpendicular to V. In this case, A only changes the directions of velocity vector, not the magnitude of velocity vector. Hence, this force does not do any work because it doesn't change the kinetic energy of the satellite. Circular speed VR. To find a constant speed, a circular speed of a satellite in a circular orbit with radius r measured from the center of the Earth, has to be from the center, all the r's measured from the center. We need to use Newton's second law, F net equals to ma. We know F net is gravitational force and a is centripetal acceleration. We set them equals to each other, you get VR equals to square root of gme of r. This is called a circular speed. So this relationship shows that we cannot choose the orbit r and the speed v independently. For a given r, the speed is predetermined. The larger the orbit, the slower the speed. This equation also shows that motion of a satellite does not depend on its mass. So any satellite launched in the same orbit will have the same speed. Regardless, you can have a massive one like 400 kilograms or 1 kilogram, they all have the same speed. Radius, period, and speed in a circular motion. So the speed equals d over t. D for a circle is 2 pi r, t is the period. We also know the circular speed equals to gm over r, the square root of that quantity. We set them equals to each other. We can find t equals to 2 pi times r to the power of 3 over 2 divided by square root of g times me. So this equation shows that the larger the orbit, the slower the speed, but longer the period. So here are the two pictures. One is the International Space Station, the other one is Moon. As you can see, the International Space Station travels a lot faster, 7.7 kilometers per second. The Moon, on the other hand, travels 1 kilometers per second. The period for the space station is only 93 minutes, but the period for the Moon is 27.3 days. This is because the Moon is much, much further than the satellite. So both the International Space Station and the Moon are satellites of the Earth. The Moon orbits much further from the center of the Earth than does the space station, so it has slower orbital speed and longer orbital period. Weightlessness. An astronaut on board a space shuttle is a satellite held by the Earth's gravitational attraction in the same orbit as the shuttle. So the astronaut has the same velocity and acceleration as the shuttle, so nothing is pushing her against the floor or the walls of the shuttle. The astronaut is in a state of apparent weightlessness. as in a free-falling elevator, even though gravity is acting on the astronaut. But the astronaut cannot feel this force. That is because there is no contact force acting on the astronaut. Total mechanical energy E equals K plus U. Circular orbit, V equals square root of GME over R. We know total mechanical energy is K plus U. So K is 1/2 mv squared. We plus that V, plug in that V squared in here plus U. So E for moving satellite around R equals negative GMEM divided by 2R. Total mechanical energy in a circular orbit is negative and equals to 1/2 of the potential energy. This means increasing the radius means increasing the total mechanical energy. If the satellite is in a relatively low orbit that encounters the outer fringe of the Earth's atmosphere, total mechanical energy would decrease. So E decrease, that means R has to decrease. This R decrease means the orbit will become smaller and smaller, so satellite will come closer and closer to the Earth. Eventually will hit the ground and burns up in the atmosphere. Escaping speed. To escape the Earth means its potential energy reaches maximum. So the minimum escape speed is when its kinetic energy is set to 0 because that's the minimum. So K plus U equals to 0. That means 1/2 m times escape speed plus the potential energy in that radius has to be 0. So the escape speed for any radius is square root of 2 times the circular speed. The escape speed from a spherical body with radius r is square root of 2 times greater than the speed of satellite in a circular orbit at that radius. Here is an example. So suppose we want to place 1,000 kilogram weather satellite into a circular orbit 300 kilometers above Earth's surface. What speed, period, and radial acceleration must it have? So first, we have to find R. R is the distance from the center. We have to add 300 kilometers to the radius of the Earth. So that's R, 6.68 times 10 to the 6 meters. Next one, we can find circular speed. Circular speed is GME over that R, give you 7,720 meters per second. That's the speed, circular speed of the space station. Next one, what's the period? Period equals to 2 pi R over V. So we plug everything in, you'll have 90.6 minutes, about an hour and a half. And what is the radial acceleration? Radial acceleration is G, is also equals to Fg over m, also equals to centripetal acceleration, which give you 8.92 meters per second squared. As you can see that as the satellite moves away, its gravitational acceleration is decreasing just like its gravitational force. Next one, how much work has to be done to place this satellite into the orbit? So the work done equals to change in total energy. So on Earth's surface, total energy equals to just potential energy because the satellite was at rest. When you launch it into orbit, the total energy is negative of 2 GME times m divided by 2r. So the difference between those two, E2 minus E1, is 3.26 times 10 to the 10 joules. Now, how much additional work would have to be done to make this satellite escape the Earth? So remember, to escape the Earth means the minimum total energy is 0, E3 minus E2. Escape total energy is 0 minus E2. What is E2? E2 is negative GMEM over 2R. So this is what it is. So you will need additional 2.98 times 10 to the 10 joules of energy. Test your understanding. So your personal spacecraft is in low altitude circular orbit around Earth. So air resistance from the outer region of the atmosphere does negative work on the spacecraft, causing the orbital radius to decrease slightly. Does the speed of the craft remains the same, increasing or decreasing? Let's take a look. V equals to GME over R. As R decrease, V actually increase. So the answer is increasing. Okay, So the answer is increasing. That's it for today. Thanks for watching. See you next time.